Welcome to Learning Chemistry with Faye. In this video, we will learn how to determine an unknown compound's molar mass using ideal gas law. Let's first look at what is ideal gas law. Ideal gas law is using the relationship of different variables that you can control in the environment to determine the unknown variables. So in this case, we are going to use all the variables that we can see here in this equation to determine an unknown compound. Ideal gas. So what are in ideal gas law? You have pressure, volume. N is represented as the number of moles of the molecules within that volume. R is a constant and is equal to 0.08206. And T, of course, is the temperature. So with these, remember the R constant is this particular number only under the units that you see here, with the pressure in atmosphere, volume in liters, mole numbers as mole, and temperatures in Kelvin. So can you have a different R constant if you change the units of the variables in here as, for example, in pressure? Yes, you can. Okay, the only thing that wouldn't really work is if you change temperature in any other units. So that means if you have a temperature relationship in a particular situation and you wanted to calculate any other variables according to temperature, you want to make sure your temperature is in the units of kelvins. So how are these quantities related to each other mathematically? What are their relationships? Here is a trick. If you want to identify how are they related, how are the variables related, all you really have to do is look at which side of the equation that they're on. If they're on the same side of the equation, okay, so for example, it's P and V, they are inversely related. That means if one goes up, the other must go down. Because if you assume everything else on the other side of the equation is a constant, on the same side, the variables on the same side has to balance out each other to make the other side constant. So that means if it's on the same side of the equations, the variables are inversely related, which means if one variable goes up, the other must go down. And if the variables are on different sides of the equation, then they are directly related, which means if one goes up, the other also has to go up. So for example, if you have P and T, right? So if you want to see what's the relationship between P and T, with all the other variables with N and volume are constant, then if a P goes up, if a pressure goes up, your temperature has to go up. And then we call that directly related. So you just assume N and V and R, you kind of put them in a format of constant referred by K, and then P would equal to T multiplied by a constant. So if this is if your K is a constant, then that means if your P goes up, your T has to go up. So they would stay consistent. Okay. And with that, if you have a constant, you can also drive this further with multiple or with the change of the environment to calculate equations with the different environments. So for example, if you have one setting or you started with the initial settings of a pressure or you started with some kind of initial settings of a temperature, and then you keep everything constant, everything else constant as the mole numbers and the volume, and you want to calculate the change of temperature, how would it affect the change of pressure? you can, because they're inversely related, they're directly related with a constant. And that also leads to a different law. In this case, we have P1 over T1 equals to P2 over T2. That means if assuming all other variables have the same or stays the same, stay as a constant, and you have a pressure and the temperature, and you change one of the variables between pressure and temperature, you can calculate the other pressure or temperature. So let's look at another example. So in this case, you have volume and temperature. With the mole number and pressure stays constant. So PV equals to nRT, right? So that means V and T still on the different sides of the equation. That means V and T are directly related. And you would have a similar relationship as a constant equals to V over T, which drives into a very similar relationship as V1 over T1 equals to V2 over T2. So here is called so after you guys learn the ideal gas law, you can also derive it to combined gas law, which means P1 multiplied by V1 over N1 multiplied by T1 equals to P2 V2 over N2 T2. So that also, does this also represent that if I keep N1 T1, like keep the mole numbers and temperature consistent, then I have P1 V1 equals to P2 V2? Yes, it does. Okay, so those are called, there's a Charles law, Boyle's law, and they're all derived from ideal gas law. All you have to remember is the ideal gas law. Remember when you're looking at this, what else you can do is just remember the combined gas law, and you don't have to memorize every single little details of all the characters, but remember to plug in if the question asks you, the question gives you the fact that these variables are constant. So all you had to do is comes back to this particular equation, to this combined gas law, and cross off the ones that says is constant. And the variables that's left are the ones that's either in variation or is the one that's what you're looking for. So let's look at how do we use ideal gas law. Let's look at an example of how do we use ideal gas law to determine the weight, the molecular weight of unknown compounds. So let's first look at what we will be doing in this particular experiment. So we will have a setup of you will have some kind of a flask. You will want to measure some unknown compound in this particular flask and then cap it with aluminum foil. And afterwards, we will heat it up in a beaker full of water. So there are a couple of things that you actually want to watch out for. For one thing, this aluminum foil that you're covering the flask, you don't want it to be so much that it will touch the water, or for the water to be able to get moisture hidden under this particular area. Once the water gets into your flask, it's very difficult to get out, and you won't be able to evaporate it because your unknown compound is going to be has a lot lower boiling points than your water. So you don't want that to add to the weight of your flasks. So what you will be doing is you are boiling this particular unknown compound, and you're going to poke a small hole at the on the aluminum foil. So what's the purpose of poking this little hole? You don't want the hole to be too big or too small. If it's too big, when you're boiling, your unknown compound is going to escape way too fast. Then there is no way for you to control the volume. But if it's too small, you're going to be there for a while, which is fine because it's all eventually going to evaporate. And this water level, you want it to be high enough so your flask is going to have a consistent temperature. So the volume of it doesn't just stop right where the volume that for your unknown gas doesn't just stop and recondense after you're heating it. So you would actually have a chance to escape and have a chance to evaporate. So you want it to be high enough to represent that this entire flask is the volume of the evaporated unknown compound. So in here, what you are trying to do is you are boiling this water at a slow pace. And the water will heat up the flask and evaporating the unknown compound until you see all the unknowns are gone. Whenever you see the last drop of the unknown is complete to evaporate completely, you want to stop immediately and take this flask out of the beaker to cool it, to condense, to recondense whatever all the molecules that was left, all the unknown gas that was left in the beaker. So now you know with the temperature that you evaporated all of your unknown compound, that is your temperature. That is your T. The volume is your flask. The volume is the entire flask up to where you covered with aluminum foil. That is your V. And you will also need to have the R value, right? You also have the R value. You will have a pressure measured by a barometer. And what is left, you can use these values that you have just determined from your experiment to calculate the N, which is the mole number, right? So you are going to also weigh out how much is left after everything is condensed, after your glass is cooled, and once you finish heating it, you take it out of the beaker and you completely cooled your flask. There will be some of the molecules, the unknown compound, to recondense back into your container. And then that's when you wanted to weigh it and find out how much is left, how much of the unknown compound is going to be left in this particular flask. And with that, you will have a weight. And with this weight, with the mole number, with the weight that's given to you, you will be able to calculate the molar mass of your unknown compound. So let's look at an example. Okay, so you have a bubble, okay, and then you know the value, the volumes of it is 284 milliliters. So a 284 milliliters bubble contains 0.177 grams of unknown gas at 0.951 atmosphere and 25 degrees Celsius. And we want to look for the molar mass of this unknown gas. So let's look at this unknown. Okay, so what do we have? So we wanted to calculate the molar mass, right? We're looking for the molar mass of unknown gas. And what does the unknown gas equal to? So we can only relate the molar mass of any compound in this particular law by using the mole number. Right, so it's a PB equals to nRT, and only the N can give you the direct relationship or the direct calculation variables to relate to molar mass, right? Since the moles equals to the weight that you have right here, divided by the molar mass. So that means we need to further calculate, we need to first calculate the mole number. So since we have moles equals to grams per molar mass, we can also just reverse that and make it molar mass equals to the weight that's right here given in your question divided by the mole. It's the same thing, right? So right here we can translate that into 0.177 grams over mole number. That would give you the molar mass. But how do we get to, so in this case, what we need to do is to solve for n. In order to solve for n, we need the relationships of PV equals to nRT. And then we would just shift all the other variables onto the other side of the equation, which is P1 V1 over T1 and multiply by R, right? So you have P times V over T times R. And then we have all these variables available right here, right? So R is the constant, pressure is 0.951 atmosphere. We have volume. Remember, you need to convert the volume from milliliters to liters, which is 0.284 liters. And you also need to convert your 25 degrees Celsius to Kelvin. And in that case, we can find the mole number. Once you find the mole number, you have the weight of the compound of the molecule that you used divided by the mole number, you will get your molecular weight. And in this case, we have 16.1 grams per mole. And that is the molar mass of your unknown gas. So hopefully this will help you to determine the molar mass of your unknown gas a little bit better in the lab with a given measured volume. You are going to measure, you're going to weigh out how much unknown you have after a procedure to calculate, after a procedure to find out how much unknown gas is for a particular controlled volume at a given temperature and the pressure. Okay, so let me know if this video has helped you, and if it helped, and then please post any comments that can further help you to proceed with your lab. I'll see you in the next video.